In this lesson, we're going to talk about multisets, and we're going to learn how to solve problems involving counting multisets. So first of all, what is a multiset? Well, it's a collection that can have multiple instances of the same kind of item. So remember that just regular sets, when we're talking about sets, if a set is listed like this, 1, 2, 2, 3, well, repetitions don't matter. Either 2 is in the set or it's not in the set. So we wouldn't even write it that way. We would just write it 1, 2, 3 because either a element is either in the set or it's not. So we would just write it 1, 2, 3. But when we're talking about multisets, the repetitions are significant. So I would have still looks the same with the curly braces, but 1, 2, 2, 3 means that we've got 2 instances of the 2 in there. And just like with sets, the order doesn't matter in which they're listed. So, but it does, of course, as I've said, matter. If there's more than one, it is significant. So how are we going to use this in solving problems involving counting? Well, let's look at this problem here. Suppose we want to count the number of ways to select 12 cookies from 4 varieties. So we have chocolate chip, sugar, ginger, and oatmeal. So one possible selection could be denoted this way, and this would be a multiset. We still have the curly braces, but notice we don't just have C, S, G, O. We have a certain number of instances of each. And so this multiset here, if we look at it as a multiset, then we could repeat some of the elements. So we have the C repeated 3 times, and that would represent the fact that we have chosen 3 of the chocolate chip cookies that start with a C. 2 S's would mean that we've chosen 2 sugar cookies, 2 ginger cookies, and then 5 oatmeal cookies. So that would just be one possible selection, but you could see that, imagine that we have all kinds of possibilities there. Maybe we just have all of them being chocolate chip. So we would have 12 C's in there. So what we're going to try to find out is, we're trying to count the number of ways that we could make this selection. So what we're going to do is define a bijection between the set of possible cookie selections and a certain set of binary strings called code that we're going to call code words. So remember that we know how to solve a lot of problems involving binary strings, and so what we've been doing lately is taking a situation and finding a bijection between that situation and binary strings. Then we use what we know about binary strings to be able to count the number of ways possible. So we're going to just do that again. So we're going to come up with some kind of bijection that somehow maps possible cookie selections to binary strings. And we can call them code words in this case. So here's an example of how we're going to do this. We have to come up with some correspondence. So over on the left, this would be that situation that we saw in the multiset above. There's 3 chocolate chip cookies, so look at the big circle. We have 3 chocolate chip cookies, 2 sugar cookies, and so on. So that would be this one possible selection. So how could we come up with a correspondence between a situation like this, and binary strings? Well, here's how we would do it. So take a look at this binary string over here on the right. We have, first of all, as you see in the multiset up above, I've listed the chocolate chip cookies first, sugar, ginger, and then oatmeal. So we would have some sort of order established, probably usually just in the order that they were first told to us. So here in the top first sentence, we have the chocolate chip listed first, and then the ginger and sugar and oatmeal. So we're going to stick with that order in coming up with this binary string. So since chocolate chip comes first, then we would have the number of zeros that correspond to how many chocolate chip cookies we have. So here's 3 chocolate chip cookies, so I start with 3 zeros. And then you see, forget about the ones just for a minute, go over here, you see there's 2 zeros for representing the next kind, which would be sugar, 2 representing the ginger, and then 5 representing oatmeal. So we have zeros corresponding to how many of each variety. But you also notice there's ones in there. We're using ones to separate the different varieties. So by putting a 1 in there, we're saying we're going to go on to the next variety and list how many there are in that by listing a bunch of zeros. Okay, so we have zeros saying how many of a certain variety, then a 1 to say we're going on to the next variety, and then more zeros, and then another 1. So that's what we would have here. So you see that this would be a bijection, right? Because we could go from the cookie situation to this binary strings that look like this using those rules, but we could also clearly go back, right? We could take a binary string that looks like this and interpret it then as the cookie situation. So we see that it is a bijection, and by the bijection rule, we would say that the number of distinct code words, these binary strings here, is equal to the number of distinct cookie selections. So we will just concentrate now on trying to find the number of code words possible instead of worrying about the cookies. Okay, so just kind of before we get involved in counting all of this, let's just make sure we understand this bijection that we're doing. So I've already explained that we have how we come up with that code word. But just kind of in general, remember this, that the code words are going to need the same number of digits for zeros as however many cookies are being chosen. So remember, we wanted to choose 12 cookies, and there are 12 cookies. There are 12 zeros in there. But then, how many ones would we need in there? Well, there were 4 varieties, right? 4 varieties. So we needed 3 ones, right? 1 less than the number of varieties, because we started with the first variety, then needed to say we're on to the next, but we only needed 3 ones to make the separation of 4 varieties. Okay, so it was 1 less. So that's important to remember. We're going to be doing this 1 less, thinking about 1 less a lot. So we had only 3 digits that we needed for the ones, even though we had 4 varieties. So anyway, we had 12 digits to show the cookies selected, and then only 3 digits then to separate those 4 kinds of varieties. So the length of a code word for this situation would be 15 in all cases. We'd have those ones would be in different places for the different varieties, but we would need to have ones, 3 ones in there to show the number of cookies in each variety. Now, what if I were to think about answering this question, but not in terms of the cookies, but in terms of these code words? Well, I've got a binary string of length 15, and I just need to put 3 ones somewhere in there. And those ones then would, depending on where they are, tell me how many of each variety of cookies we'd have. So the question becomes, how many ways can we place these ones in this code word of length 15? Well, think about it this way. There's 15 slots. I'm choosing 3 of them to put my ones in. So I could take 15, choose 3. That would give me the number of binary strings that of length 15 that have exactly 3 ones. Also then, that would then, because it's a bijection, also give us the answer to how many selections we could make for 12 cookies from 4 varieties. Okay, so look at that, 12 to 4, and we got 15 and 3. Think about, remember how we got the 15 and the 3. Well, the 3 down below, that was, how many ones we need, and so that would be the number of varieties minus 1. So it was 4 minus 3, that was 1. Now, how did we get the 15? Well, it was however many cookies we were choosing plus the 4 varieties minus 1, right? It's that number down below, because we had to have that many slots to separate the varieties. So we got the 15 by taking the 12 plus 1 less than the number of varieties. So 12 plus 3 gave us the 15. So now let's be a little bit more general. Say we don't necessarily aren't necessarily selecting 12 cookies from 4 varieties, but we're selecting n cookies from m varieties. So again, just the same, using the same that same rule for coming up with a code word, we would need n zeros to represent those n cookies. And then how many ones would we need? Well, we would need enough ones to separate the m kinds of cookies, so we would need m minus 1 of the ones, right? So we have this code word here. It's going to have, we're going to need, if we're selecting n cookies, then we would have n zeros in that code word. And then how many ones? Well, as we just said, we need enough ones to separate the m kind of cookies, so we would need the m minus 1 ones. So how many digits altogether? It'd be the n plus m minus 1. That'd be how many digits we need for this example. So n plus m minus 1 digits, but remember we're placing m minus 1 ones. So we're saying how many different ways can we place these ones in this this certain length code word, and remember there's m minus 1 of them. So the way we would find that is taking the length of that code word, which is n plus m minus 1, and choosing m minus 1, because we have m minus 1 ones to distribute in there. So we're saying we're going to choose the slots where we're going to put the ones, the m minus 1s, m minus 1 ones. So hopefully you see that this is what it would be. We would find the number of ways by taking n plus m minus 1, choose m minus 1. And so that's how many binary strings we would get, and so therefore we could say that's also the number of ways that we can select n cookies from m varieties. So here we have just kind of come up with this formula just by reasoning out with this one first example with the 12 cookies. So the number of ways to select n objects from a set of m varieties is what we just saw. N plus m minus 1, choose m minus 1. Now we're making an assumption here that there's no limitation on the number of each variety available, and we're going to assume that throughout this whole section. So we're not going to say, well, they can choose 12 cookies, but there's only 10 cookies available that are chocolate chip. That would make it a different problem, but we're assuming we have, given the 12 cookies or however many we're choosing, that there are at least 12 of all varieties so that we don't have to worry about any restrictions. So that's saying this is true if there's no limitation on the number of each variety available. And also, we're assuming that objects of the same variety are indistinguishable. So like any 3 chocolate chip cookies, we would count as the same way. It doesn't matter which of those 3 chocolate chip, because we're assuming that all of the chocolate chip are indistinguishable. So let's see this in a different light. Let's look at another type of problem. We see it's not necessarily a different light, just a different situation using this very same rule. An employee of a grocery store is placing an order for soda. There are 8 varieties of soda, and they're sold in cases containing just one variety. So, the employee is going to order cases of soda, and there's 8 varieties of soda available. The store will order 50 cases total. How many ways are there to place the order? So, they're going to order 50, and there's 8 varieties. So let's see if we can think about this. How many digits would we need in our code word? We'd need the 50 digits that represent will have zeros that represent how many of each variety. So we'll need 50 zeros in there. But how many ones will be in there? Well, it's the number of varieties minus 1, so it would be 7 in this case. So altogether, we're going to have 57 digits, and then we're going to choose some of those to have 1s in them. So it would be the 57, choose 7. So again, 50 cases to be chosen, so n equals 50. 8 varieties, m equals 8. So what we just said turns out to be this formula here. N plus m minus 1 would be 57, and m minus 1 is 7. So it's 57, choose 7. And that would give us the answer, because we know that we can make this bijection between this soda situation and the code words, and so therefore but really, now that we've been given this fact up above, we don't have to I think I always still go and think about the code words, but what basically this function is saying, we don't even have to think about code words now. We can just plug this in based on that formula here. But to me, I think it's easier if I think about the code words, because then I really don't have to memorize this formula. I can come to it right away. Oh, how many digits do I need? And then how many ones do I need? So, for me, it's easier to continue to think about those code words. But if you memorize this fact here, then you don't even have to go to think about the code words. You can just think, oh, well, I'll use this formula. Anyway, so the answer here would be 57, choose 7. Now, sometimes we might have some restrictions, and so we're going to learn how to solve problems with restrictions here. So again, let's say that we have an employee of a grocery store and they're placing an order for soda. There are 8 varieties of soda, and they're sold in cases containing just one variety. So just the same thing as before. The store will order 50 cases. So that's all the same. But now here's the question: how many ways are there to place the order if this employee orders at least 3 of each variety? Okay, at least 3 of each variety. So here's how we might go about it. Let's think about setting aside 3 cases of each variety. So it's basically, think about as she goes in and pulls out 3 cases of each variety, sets those aside, saying that I'm getting those for sure. So that's the given. Now we have to think what's left for her to, how many more does she have to choose? And then how many ways of making that choice? So if we have 3 cases of each variety that she's taken aside, and there's 8 varieties, then that takes care of 24 of the cases. And remember, she's only ordering 50. So that means that we would just realize 24 of these are going to already be chosen because of this restriction. So that just leaves the 50 minus the 24, which is 26, really leaves only 26 cases to select now, where there is an option here. So now the 50 then has gone down to only being 26, because there's only 26 cases that we have these different options for. So now the selection has become 26 cases need to be chosen, and again we have 8 varieties. So N is 26, M is 8, and so we can use that formula. N plus M minus 1, choose M minus 1. Or again, think about it as the code word would need to be the 26 zeros plus the 7, 8 minus 1, 7 ones. So it would be the 26, the 26 plus 7 would be the 33, and then but we're choosing the ones in there, choosing the slots where the ones go, and so there are 7 of those. So it would be 33, choose 7. Okay, here's another type of problem that looks very different, and yet we can solve it just the same way. Consider that we have the equation x sub 1 plus x sub 2 plus x sub 3 plus x sub 4 equals 12. How many solutions are there to the above equation if all of the variables are non-negative integers? So that means it could be 0. Any of those could be 0. If it's non-negative, it can be 0. Or it can also be, anything bigger than that. Okay? So, but we can't have negative. So it's not like we can have like a 13 as one of those values and then back it up with a negative number in order to get the 12. So all of these numbers that have to add up to 12 are non-negative integers. Well, if you think about it, that's exactly the same problem as the cookie problem, right? Because we were choosing 12 cookies, and we could choose 0 oatmeal if we wanted to, or any of the varieties. We could choose that we don't want any of them. So any of the numbers of variety, any of the numbers of cookies from a certain variety could have been 0, and then or it might have been 1, it might have been 2, and so on, and we had to add up all the number of each variety chosen to give us the full 12, right? So it really turns out that it's the same problem. So x sub 1, if we had this one situation where we have these values, x sub 1 is 5, x sub 2 is 0, and so on, then that represents, that we could, create a bijection between this and the cookie situation. So if x sub 1 was 5, we could say that that would correspond to a selection where we have 5 of the first variety, and then 0 of the second variety, and 3 of the third, and so on. So we could look at that as a bijection. Also, we could go back to the code words, which again I think I would do. Think back, rather than memorizing this formula, I would think back to, well, I could come up with these code words, and again, how many possible slots do I need? How many ones do I need? So I would need the 15 slots, the 12 plus the number of ones I would need, which would be 4 minus 1. And then where do those, which positions do I place those 4 minus 1 ones? And there would be 3 of those that we choose out of the 15. So it turns out again to be 15, choose 3. But again, If you want to, you could just memorize that formula and use that. Now this is going to be a little different, and it's really important when you see a problem like this in zyBooks or on the test, where you keep track or make sure that you notice what they're saying. Here it says how many solutions, it's the same equation, how many solutions are there to the above equation if all the variables are positive integers. So positive is different than non-negative, because positive means we can't have any of them being 0. So it needs to be 1 up through. So we can't just use that formula straight off, because we are limited. We have to have each of those be at least a 1. So, but that's similar to saying we want to choose 12 cookies from 4 varieties where there must be at least 1 cookie from each variety. Or the case of the soda, ordering the soda, where we need a certain number of cases of each variety, right? So we can kind of look at it that way too. And imagine if we're talking about cookies, then imagine, well, we're choosing 12 cookies from 4 varieties where there must be at least 1 cookie from each variety. So just like we did with the soda, we'll say, well, let's go ahead and choose those 1 cookie of each variety first. Get that out of the way. So we'll choose 1 cookie from each of those varieties, and that takes care of our 4 cookies. So that didn't involve a choice given our restriction. We went ahead and wanted 1 of each. So that took care of the 4 cookies. So really our choices now, the different possibilities, come down to how are we going to choose those remaining 8 cookies, right? We already chose 4 of them. So there's 8 cookies left to select. So now it comes down to that we have the problem where we've got 8 cookies that need to be chosen out of those 4 varieties. So again, we would think about it, if we want to think about the equation, we could think about it in terms of these numbers, x of 1, x of 2, x of 3, x of 4 need to be, all any numbers now, right? They can be zeros now, because we've already chosen the 1 cookie from each variety. So now we're back to being able to solve it like we did before, where we just need to choose 8 cookies, or 8 cookies, or in this case, have 4 numbers that would add up to 8 instead of the 12. Okay, so we're going back and forth between the equation and the cookies. So let's think back, though, again to the cookies. So we've got 4 variety of cookies. So M would be 4, but we're choosing now just 8 cookies. So we would have, again, this is the formula, but we could think about it in terms of there's 8 cookies need to be chosen, but then we need 3 ones to separate the 4 varieties. So it would be the 8 plus the 3. So we'd have 11 slots if we're thinking about slots in the code word. 11 slots, and we need to distribute the 3 ones. Again, because there's 4 varieties, so we need 1 less. So anyway, it would be 11 choose 3. So hopefully this is making sense. But again, I just want to point out, remember this question at the top here looked very similar to the question on the last slide. It's just that one of them said non-negative and the other said positive. So the fact that we said positive here meant that we needed to choose at least, make sure each of them was at least 1. So that's why we started thinking about cookies again and said, let's separate the cookies out. 4 of them, we already need 1 of each. And so then that took us down from a choice of 12 to a choice of 8. Okay, so sometimes we might have a problem like what we've just been talking about, but we have some kind of restriction so that it turns out that we might need to use this complement rule that we learned the other day, where we don't know how many situations there would be in this one, whatever the circumstances are, but we know how many. We could easily find out how many would not have that certain situation, and then we subtract that from the total number of possibilities. So let's read this and see a problem like that. An employee of a grocery store is placing an order for soda. There are 8 varieties of soda and they're sold in cases. The store will order 50 cases total. So that's kind of what we've already been looking at. But now here's the question. How many ways are there to place the order if she does not order more than 20 cases of Coke? Does not order more than 20 cases of Coke. So that means she could order 20 cases or 19 cases or 18 cases, or even 1 case, or maybe even 0 cases. So we've got all kinds of possibilities here. But we could look at earlier and think about what we did earlier, and that's using the complement rule. So if we're going to use a complement rule, we need to find out how many ways there are with no restrictions. So if we didn't have that restriction, what would it be? We just had that first sentence there, we're just choosing, placing, an order for 50 cases. Then we saw that it would be 57, choose 7. Okay, so that's without these restrictions. But now let's look and see how many ways there would be if she does order more than 20 cases, because remember, we're going to try to use this complement rule, and the question is how many ways if she does not order more than 20 cases of Coke. But let's see if it would be easy enough to find the answer to this. How many ways if she does order more than 20 cases of Coke? Well, that comes down to a problem like what we've done in the past, where we'll say we'll set aside a certain number of cases that we want to make sure she chooses. So if she wants to choose, if she's going to order more than 20 cases, then let's have her set aside 21 cases of Coke. That way, at least for sure, she has more than 20 cases of Coke. So set aside 21. So that leaves now only 29 cases for her to select. So it's now become a problem where she's selecting 29 cases out of 8 varieties. So N would be 29, M would be 8, and then of course we would take 1 minus M, in our to consider here in our formula here. So the number of ways to place the order would be that N plus the M minus 1, so 29 plus the 7, and then choose the 7. So 36, choose 7. Again, you could look at it as there's 29 zeros to place and 7 ones to place. So the 29 plus 7 gives us how many, if we're looking at the code words, that's how many digits. And then we need to place the 7 ones, and so we're choosing out of the possible 36 slots, we're choosing 7 of them to place the ones. So again, it comes down to 36, choose 7. But that's just answering the question, how many ways if she does order more than 20 cases. So now we need to answer the actual question, how many ways are there to place the order if she does not order more than 20 cases of Coke? So we take the number of ways to order with no restrictions and subtract the number of ways to order if she does order more than 20 cases of Coke. And that will give us our answer. So it would be that first answer we got, the 57 choose 7 up above, minus the 36, choose 7. And that would be the way we would leave it. Now for zyBooks, you would probably put they would probably want you to put the capital C and then 57, 7 minus capital C and then the 36 minus 7 in parentheses there. So, but that's how we would leave our answer. So hopefully you see this again. This is by counting by complement. We found the easier way first and then did the subtraction, and that gave us our answer. Okay, we have one more scenario that ends up being equivalent to this cookie situation. Okay, so suppose that we've got 12 indistinguishable balls. They're all the same, are placed in one of 4 bins. The bins are numbered, so the bins are distinguishable. Okay, so we're saying there's a certain bin called bin 1, there's one called bin 2, and so on. And so putting 8 balls in bin 1 and 2 balls in bin 2, like we see here in this picture down below, that would be considered a different configuration than if we put the 2 in bin 1 and the 8 in bin 2. Okay, so that's just what we mean by distinguishable bins. These two placements would be considered different because we have different number of balls in the particular bins. Okay, so what we want to do is find out how many ways we can place these 12 indistinguishable balls into the 4 distinguishable bins. Well, it turns out, you know, that there's a bijection between placement of balls into bins and the number of ways to select 12 objects from 4 varieties. Because just think about this, you know, let's look at this this scenario over on the left here with the 8 balls in bin 1 and then 2 and then 1 and 1. The fact that we have 8 balls in bin 1 could correspond to the fact that we're choosing 8 cookies of the first variety and then 2 cookies of the next variety, 1 of the next, 1 of the next, and they have to add up to however many we have, and in this case it is 12 again that we're looking at. So hopefully you see that, you know, it's really the same situation. Balls in bins versus choosing cookies, because I have the 12 to choose from. Either I'm choosing which variety of cookies I want, or I'm choosing which bin to put these balls in. Okay, so here again now is a new fact. Indistinguishable balls and distinguishable bins. The number of ways to place n distinguishable balls into m distinguishable bins is this. Same formula. So on that last problem, we really didn't go on and actually put the numbers in, but I think you could finish that last problem off now knowing that you can still use that same formula. Okay, so now there's some additional exercises that you can do for extra practice. The second additional exercise in there is one that you can do, and I've opened up the solutions for that. And then the 6th exercise, parts A, B, and C, you can do that also for extra practice. So try to do those yourself before looking at the answer, see if you got the right answer, and then you can look at the solution if you're not sure how to do it or if you got the wrong answer. And then do that, and of course do the participation exercises that are in this section. I don't think there's any challenge exercises in there. Now we have one more lesson next time that we're going to cover before we're ready for the test, our next test. So our test isn't until after we cover this one more section. But some people were asking if they could go ahead and start looking at the study guide. I had mentioned that there will be a study guide that kind of tries to break things down for you, gives you a lot of examples to try, and also gives you some ideas on how to study in distinguishing the different types of questions, since, as I said early on in this unit, that all of the questions for this test will just be how many different ways can certain situation be, be accomplished. So there's just a bunch of these types of questions. So I think this study guide should really help you. So I would definitely, if I were you, try to spend a good amount of time on this study guide, going over each problem and looking at seeing if you could come up with that, not knowing from which section it comes, because that's what'll happen for the test. You won't know. You'll just be given all of these questions, and you have to be able to think, which formula would I use, or which, how would I think that through? And so that's why this study guide, I think, will be really helpful, because you have all these problems, and then you just have to try to, practice figuring out which category each of those problems are in. Anyway, so some people were asking if they could get a hold of that now, even though we're not done. So I have I've posted the study guide, not under this week, but under next week. So if you want to go ahead and start looking at that study guide, you can. Just know that there is still one section we haven't covered. Okay, so feel free to look at that if you want to now. But definitely after we cover that last section, you want to spend some good amount of time on the study guide.